Hello everyone, welcome to the video lecture. So today we are going to talk about one of the statistical technique which we call it t-test. But before starting, let's recap what we have discussed so far. So far in our class, we talked about the importing data, exporting data, all the basic stuff in SAS. Then we worked on to how to create different type of reports with the proc print function, how we can apply some type of formats to the data, to the output. And also then we talk about all the descriptive statistics. So we will talk again more later in following sessions. For example, for descriptive statistic, we learn how to work with proc mean, proc freq for the numeric variables and also the character variables. And then we talked about the bigroup processing, how we can deal with certain type of group of people, for example, certain type of group of observation in our data. And also the managing data, transposing the data set function, how we can merge data, different type of merging, and how we can create some different type of graphs, pie charts, stack bar charts, bar charts, all the type of graphs that we already seen so far. So today we are gonna talk on the t-test. So we have three different type of t-test that we will discuss about it today. So the first one, the single or one simple t-test, the paired one, which is the dependent one, and the last one, which is the independent t-test. But what is t-test? So for example, imagine you're doing the heart transplant surgery and you would like to know what is the difference, for example, between the group of male and female. Are this type of surgery, for example, is more effective on female rather than male, or whatever type of difference between them? Are they significantly different? Or, for example, you have two different group of, for example, patients, and you are giving them, for example, two different medication, drugs, and you would like to know, for example, which group has a better performance according to that uh, medication. So that's the type of things that you need to test with some certain uh, limit of people, for example, 100 people, 200 people. And then according to that result, you would like to generalize your result to the general population, to the main population of the people. So with some confidence level that we will talk about it, we can, for example, say with 95% confidence interval, we can say, okay, this medication works for group A better than group B. So then for the generalizability, we can say, okay, the medication A in general is better than medication B. So technically, the t-test in general, especially right now, the first one, the one sample t-test, it is used to test some hypothesis about the value of the population mean. Okay, so the mean is this the mean that we are talking about? We want to know that the mean of our sample, okay, are significantly different from some hypothesis value in the main population. So where does this hypothesis value comes from? For example, you can find it, let's say, in some NIH report or some different health reports, or for example, some article publications from the experienced people. So, for example, you would say, I don't know, the blood sugar, for example, the average is, I don't know, 100. So, you for your certain type of group of people, you would like to know that the average of your population is it significantly different from the main one, from the that hypothesis value. So that's the type of test that we would do with the t-test. So we will talk about an example and you will understand better. So before going further, again, in order to have a shorter video, all the syntax in this PowerPoint, like the previous sessions, I'm not gonna run them on SAS. They already ran, and you can see the output and also the syntax. So make sure to run it on your site definitely, and then try to see the different type of results according to the syntax. So there are some assumptions that you need to make sure to have before running the t-test. The main and the most important one is the t-test is based on the assumption that the population that you have are normally distributed. So as you see in the graph, we already talked about the normalized distribution. So we don't want to have that much skewness in the data, okay? So we don't want to have it, for example, that much to the right or to the left skewness version. So in order to find out that the data is normalized, we know that we can run the proc univariate uh, function. So the proc univariate function, data equal whatever data you have, and then we will see in the example in the syntax. So if you want to know that the data that's normally distributed or not, you need to look at the skewness and kurtosis factor in the output. I will show you. So for those, the cutoff point is 2. So if they are less than 2, you can say, okay, my data set is normally distributed. There are different cutoff points sometimes for the kurtosis, especially if it's less than absolute value of 9, it is still acceptable. But the conservative one is less than absolute value of 2. So if it's, for example, -1, 1, -2, 2, the absolute value, if we are less than absolute value of 2, we can say our data is normalized and also normally distributed. So the t-test, which we showed with the t or student distribution t-test. So as we see in the formula, it's equal to the x bar minus mu 0 divided by the standard deviation uh, divided by the square root of the sample size. So as we know, the t is the t statistic, t test statistic, and also the x bar is the sample mean, the population that you have that you would like to compare with the main population. So that's considered as the x bar, and the mu null or mu zero is the hypothesis of the population mean. For example, uh, like the one that I mentioned, that you can, for example, have it from some main resources like NIH report or whatever. That's technically some information regarding the main population. And in the questions in type of other type of assessment, they will give you that mu null value, and the s divided by the square root of n, that one considered as the error of the data. So we can run this one again. As we know, this is not a statistic class, so you don't need to, for example, calculate this formula with hand with some numbers. So the SAS is gonna give us all the results. The only things that we need to know is how to interpret the result that we will see. One point that we need to understand, there is a one concept that we call it as a degree of freedom. Okay, so let's first know that the t-test has the n minus 1 has the n minus 1 degree of freedom. So for example, if you have 20 sample in your population, in your sample size, the degree of freedom is 19. What does it mean? Let me give you one simple example. Imagine you have a soccer team and you have 11 player and you have to assign position for this 11 player, okay? So when you want to put the first player uh, into the field, you have 11 position available for the for that a specific player. When you want to put the second player, now you have 10 position available. The third player, 9 position available until the last one. For the last one, there is only one position available. So there is no uh, freedom for that last player to choose any different type of position. Just one left for them, and then you need to assign that one to the last one. So technically, it means for your population, for the number of the size is n minus 1 has that freedom to vary differently. One is going to be fixed for the last position left. So some key points about this one, make sure to read this one. So again, the t-test follows the student distribution with the n-1 degree of freedom, which account for the sample size and allow for the smaller sample size. So the numerator again represent the difference between the observed sample mean, the population that we have, minus the hypothesized mean, which the one that we get it from the, for example, those valid resources. And the denominator is the standard error of the mean, which measure the variability of the sample mean relative to the sample size. So we will talk how we can work with this one and accept the null hypothesis, alternative hypothesis that I will show you in the following slides. So let's see this example, and it's gonna make more sense for you. So imagine the average of the IQ of the college undergraduate in the US is 100, okay? So that 100 is exactly that mu zero or mu null that I mentioned. Let me. So this mu null, the one that I said is a hypothesized population mean. In this example, as we see, it gives us that value is 100. A researcher believes that the students in a Great Valley College have the different IQ than the national average. You see, they didn't mention that they have the higher or lower. They said just it's a different one. So she collects information on the IQ scores from 19 students, undergraduate students, and find that their average of IQ score is 108, okay, with a standard deviation of 10. So now they would like to know that are these difference are significantly different or not. It means that it shows that the average is higher than, but we need to test it with the t-test to see that these difference are significantly different or not. Can we generalize to the larger population? So in that case, we have to do the test. So we need to know that is the mean of the IQ scores of the undergraduate is different than the national average. Maybe now you are saying that, okay, it's 108, that one is 100. So for sure it's different. Yes, it is different. But the main point is we need to know that are they significantly different. So in that case, we need to run the t-test. So another example, we will go back to this example in the following slide. A researcher are interested in whether the pulse rate of the long distance runner differed from that of other athletes. They randomly sample 8 long distance runners, measure their resting pulse, and obtain the following data. So the average resting pulse of the athletes in the general population is 60. So again, this 60 is that mu null or mu zero beats per minute. So we need to test the null hypothesis at the 0.05 level of significance. So this 5% or 0.05 level of significance is the p-value of the level of testing, level of significance. So we need to compare with this one. So in order for the p-value, I will make sure to also post some video for you on D12, so you can watch and see what does it mean in general by p-value, and I will also explain in this video as well. So we want to know the statistical difference between the sample mean and a known or hypothesis value of the mean in the population. So for example, the one that we had, the average IQ of the main population was 100, okay? So if you remember, I mentioned that they're asking that if the IQ is different from the main one. They didn't mention is it lower or higher, okay? So in that case, we can test our sample size, our sample in two different sets, one-tailed or two-tailed. So for the two-tailed version, we can say, for example, the IQ might be over 100 or less than 100. That's the two-tailed test. But if you say, for example, I just want to know that if their IQ is over 100 or just less than 100, that's going to be a one-tailed test. We will see in the example. So this is the way that we run the hypothesis. So we have H null and also H1. H null is the null hypothesis. H1 is alternative hypothesis. Okay. So for the H null, we always mention that, okay, the average of our population, our sample population, is equal to the average of the main population. This is always a null hypothesis. And if we want to show that there is a difference between these two groups, we want to reject the null hypothesis with the t-test result. If with the t-test result, we can prove that, okay, right now, it shows that there is a significant difference between these two groups. Now we can say the H null, H0 is rejected. So we are going to accept H1. So technically, we can say, okay, now we know that the average of our population is different from the average of the main population. Some maybe it's lower than, some maybe it's greater than. Okay, so that's the type of thing. So the left tail, the one tailed, we can say that if the IQ is less than 100, so now for the alternative hypothesis, we would say the average of our population is less than the average of the main population. For the right tail, we would say IQ, for example, is over than 100. So the alternative hypothesis is average of uh, our population is greater than average of the main population. And for the two tail, we would just want to know that they are different. It doesn't matter, greater than or lower than. Okay, so that's the way that we can do the hypothesis testing with t-test. We will see in the example how we can interpret from the result. So if you remember, I mentioned about the p-value or alpha. So we have different type of p-values, 0 0.10, 0 0.05, 0 0.02, 0 0.01. So these numbers are the fixed value. We usually go with the p-value of the 0 0.05. So technically by 0 0.05, we are testing with that confidence of 95% that according to that 95%, we would say, okay, we can reject the null hypothesis or accept the null hypothesis. Okay, the one that related to the how they are equal, the population of the our sample, the population, sorry, average of the our sample and average of the main population. So, for example, this is the way that we can read this table. If the question, which they will tell you, for example, calculate with the significant level of 5%. So you choose the 5%. If it's a two-tailed, which means this one, or right tail or left tail. So for the two-tail, if your value of the t-test, okay, just listen. If your value of the t-test is greater than 1.96 or less than minus 1.96, then you can say that, okay, I'm gonna reject the null hypothesis. If it's a right tail, left tail, it's if greater than 1.645, we can reject the null hypothesis and accept the alternative hypothesis. And also for the left one, if it's again greater than minus 1.645. So we will see in the example, it's gonna make more sense for you. So if it's a 0.01, we can see that the value is getting higher. So we are more conservative. So technically, we need to accept it with 99%, let's say, confidence. But for this one, we are still make some room for some mistake for 5%. This one is just 1%. So we will see in the example. So technically, one more time, the t-test that we have the estimate of the our population minus the value that we hypothesized divided by standard error. So this is the let me hide this one. Okay. So this is the example. Make sure to run it on your side. So this is the data sets that you need to just copy and paste in your SAS. So it's about just the time, let's say the time of the when the student discharged from the, I don't know, after the first visit, let's say 43 minutes, 90 minutes, 84 minutes, it doesn't matter. And these tells us to read all the uh, data. So technically, for t-test, we have proc t-test. That's the function for it. And the data, which is the time data in the Hossein library, the one that I just created. Make sure to create your own library. And the hypothesized value, or that mu zero or mu null, the one that I mentioned, you need to have it from the, for example, you need to have it from the, for example, the main source, NIH report or whatever report. Okay, so that one here is 80, and the site is equal to 2, which means we are doing the two-tail test. If we would like to have just a right tail, we go with the U. If we are going to have with the left tail, we go with the L. Okay, so that's the difference between these two. So if we use site equal to U, this indicates that we want to test if the sample mean is more than 80 days. Sorry, these are days, not the minutes. And if we use the site equal to L, this indicates that we want to test if the sample mean is less than 80 days. And the variable is time. This is the variable that we are testing, and run. And this ODS graphics on, ODS graphics off, it's going to create more graphical report for us. After running this one, so now this is the t-test procedure, and this is the result. First of all, we have 20 population in our 20 sample in our population. And as we see, the degree of freedom is 19, 20 minus 1. The average of our population is 89. The standard deviation is 19. Standard error is 4.428. This is just descriptive statistic, minimum, maximum. And we can see that the t-value here is 2.30. Okay, let's go back to the table. Sorry. So as we see in this table, right now for the 5% of the p-value, we have the 1.96 for the two-tail. This is the cutoff point. So right now in our result, we can see that the t-value, okay, let me just show. So the t-value right now is 2.30. 2.30 is, sorry, is greater than 1.96. Okay, 1.96 is the cutoff value for the alpha equal to 0.5. And also we can see that the p-value, which is a 0.03, is less than 5%. So the significant level is less than 5%. As long as we are less than 5% in that position, we can say that we are in a significant level and we can reject the null hypothesis. Also, again, like the table that I mentioned, if our t-value that we calculated is greater than the cutoff point, it means there is a significant difference between the sample mean and the population mean. So technically, it means we are rejecting null hypothesis. So that's the rule you need to remember. You need to understand it. One more time. The t-value is 2.3. The significant level is 5% in this question. So the cutoff value for that 5% for the two-tailed test is 1.96. 2.3 is greater than 1.96. And also we can see that according to this one, we expect to have the p-value less than 5%, which it is 0.03. So right now the t-value is greater than the cutoff value for the 5%, and also the p-value is less than 5%. So technically it shows there is a significant difference between the sample mean and the population mean. So we can reject this null hypothesis. The null hypothesis, we assume that the population mean and the sample mean is equal. Now we can see, according to the t-test, is not equal. So let's reject H null and accept the H1 or H alternative. So technically we can say, okay, the population mean and our sample mean are significantly different from each other. Also, as we see, there is a 95% confidence interval level average. So the mean of our data, the average of our data is 89, but the 95% confidence interval is between the 80 and 98. So it means with the 95% confidence interval for the mean ranging from the 80 to 98, this interval suggests that we are 95% confident that the true population mean lies within this range. So as we see here, the data is almost, let's say, normally distributed, and we can see that confidence interval uh, here, and also this is the 95% confidence because the alpha is 5%. So if you remember, we mentioned that for checking that if the data is normalized or not, we can check it with the skewness and kurtosis. So the function for it, again, is proc univariate, the one that we had already in the previous session. The data is the time from the Hossein library and then run. That's it. The report, again, some statistical items we will see, but we can see that the skewness is minus 0.7 and the kurtosis is 0.6. So technically, these values are less than absolute value of the two. So we can say, okay, our data is normalized, distributed normal. Okay, so after do all the calculation for the t-test, now, for example, you need to write some reports for whatever people that you need to report, okay? So the type of reports, I'm gonna read it for you. So it's gonna be look like this. So for example, you did some t-test, one sample t-test, in order to determine whether the depression score, for example, in this example, is recruited, was different from the normal people, okay? So defined as a depression score is 4. So depression score were normally distributed as assessed by the skewness and the kurtosis. And also you also already check the depression score for your population, which is 3.73. So is lower than the normal depression score of 4. And then you did all the t-test stuff, and you found that, okay, the t for the degree of freedom of the 39, which the population mean is 40, so degree of freedom is 39, is minus 2.381. So technically this one again is greater than uh, is less than the value of the alpha, and then with the p-value of the 0.02, which is the less than 0.05. So technically you would say, okay, we are rejecting the null hypothesis and accept the alternative hypothesis. In that case, you can say, okay, our population mean is significantly different from the sample mean. Now let's go to the second type of t-test, which is for the paired sample or dependent sample t-test. Okay, so in that case, you have different group of observation. For example, you are comparing the pre-test and post-test score in the educational data, or for example, before and after of the measurements in the medical studies, or for example, planned agricultural experiment where two variants of seeds, fertilizer, etc., are used on part of the same plot. So that's the formula for it. So this time again, the t-test, we have the d bar. So d bar is the mean of the differences between each pair of observations, okay, between these two groups. And d null or d zero is the hypothesis mean, the hypothesis mean difference, which usually we consider it as a zero, uh, because we are testing whether there is no difference between these two. And the standard deviation of the difference CD divided by square root of n, the number of pairs. Okay, so the number of pair matters. And again, the degree of freedom is n minus 1, like the one that we had in the single test. So again, you're assuming that the sample size are normally distributed. We can check it with, again, vertices and the skewness from the product univariate function. And we are also assuming that each pair of data used to form a difference is independent. So this is the way that we can hypothesize this one. So again, if we are assuming that just there is a difference between them, we don't mention that this is the greater than or less than. So we go with the third one, which is the average of our population is a difference between the average of the population is equal to d null, which is the zero, and this one is not equal to the zero, which means there's a difference. And also, if we have the one tail, left tail, right tail, again, we can have the same one. So for let's say, for example, if you would like to do the for the right tail, in the null hypothesis, it's going to be different direction, but still we have the equal, less than equal of the zero. And if this one, if we can reject this one, we can say, okay, now the average difference is greater than zero. And also the same for the right tail as well, for the left tail as well. So as I mentioned again, we can have the left tail, right tail, and two tail. And again, the d null represents some constant value, which usually we consider as a zero. And because we are looking that there is any difference between these two means or not. So that's why we consider that d null as a zero. So this is the example for the pair t-test. Suppose your data contain the variables weight before and weight after of some specific diet for 8 subjects. So the appropriate analysis for this data is pair t-test, because again, we are comparing one group of people in two different situations, before the diet, after the diet. So they are dependent, as you see. And the calculation for this test can be performed using the following SAS code. So again, the data weight in the Hossein library, the input is going to be weight before, weight after, and dateline is these numbers. These are the before version, this is the after version. And I would like to also first have the product mean to know the average for these two groups. And then this time we have the proc t-test again, data weight from the Hossein data side. We would like to have the two tailed, so equal to 2. The alpha is 0.05. And then we just mentioned it's a paired one. So in the previous one, so we just have product test data h null equal to 80, and side, that's it. That's a single one. But for the paired one, so we have the paired statement here, which is gonna be a weight before asterisk weight after. So this means we are comparing these two groups together. So just two things. First, the ODS graphics on off was for showing more graphical things to us, and the ODS RTF close. So if you run this code, it will automatically generate the RTF Word document you're gonna have the output in the Word document as well. So RTF is for creating a Word file. PDF, if you change it to the ODS PDF, ODS PDF close is gonna create a PDF file for you. So now that's the difference. First of all, from the product mean data, we can see, okay, there is a average for the weight before and weight after. 214 is the average of the before the diet, 199 is the average of the after the diet. And now, through the test, number of observation 8, the mean is 1525, the difference between these two, the standard deviation, error minimum maximum, and then the degree of freedom, again 8 minus 1, which is 7. Let's do together. T value is 0 0.94. 0 0.94. The cutoff value for the alpha equal to 0.5% or 5%, 0.05 was 196 from that table. Again, t value is greater than 0.96. And also we can see that the p-value, which is 0.05, is also less than 0.05 or 5%. Again, this one greater than the cutoff, this one less than the p-value. It means there is a significant difference between sample mean and population. Just let me clear something for you. These two are related to each other. If this t-value is less than 1.96, you will absolutely receive some p-value greater than 5%. But now you can see 3.94 is greater than 1.96. So we expect to see that p-value less than 0.05. So technically we can reject the null hypothesis. So we can say there is a significant difference between our group, uh, between these two groups. I just corrected this one. So there's a significant difference between these group mean, these two groups, the weight before and also the weight after. So again, we can see that data is normally distributed. So if you run it, see the kurtosis and the skewness, you can see that these values are normally less than absolute value of 2. So they are normally distributed. So again, that's the type of reports that you can write. You can address that, okay, this is the, for example, data is normally distributed. The skewness and the kurtosis, as you can see here, they mentioned that the kurtosis less than 9 is also is an okay thing. So they also cited. And then they mentioned about the t-value, the p-value. This is how you can report. The last group, which is the t-test for independent sample. So the independent t-test, which is also again two sample t-test, but is independent, is used to compare the means of two independent groups to determine if there is a statistically significant difference between them. As an example, for example, let's say we are testing a new drug for blood pressure reduction. Suppose you're a researcher testing a new drug to reduce the blood pressure, and you have two group of participants. So the first group, which is the treatment group, the participant that received the new drug, and the group two, which we call them as a control group, the participant who received the placebo. So after a month, you are gonna measure the blood pressure of the participant in both group and want to determine if there is a significant difference in blood pressure between the treatment and the control group. So that's how you have to again hypothesize. You need to have the null hypothesis and alternate hypothesis. So uh, again, we are assumed that our data from two groups are normally distributed and they are independent from each other. Okay. So that's the type of, again, a hypothesis. For example, for the example that we were mentioning, the treatment group, the control group, for the null hypothesis or H0, we would like to see there is a no difference in a mean or average of the blood pressure between the treatments and the control group, which is gonna be the mu1 minus mu2 equal to d0, which is the 0, 1. So if we consider this one as a 0, technically it means mu1 equal to mu2. So you can also hypothesize this way. In that version, we are gonna have h1 as a mu1 not equal to mu2. Okay, so you can also hypothesize in this way. And the alternative hypothesis for that one, there is a significant difference in the average of the blood pressure between the treatment and the control group. So after collecting the data, you have to uh, do the two sample t-test, which is this formula. So x bar 1, x bar 2 is the sample mean of the treatment and the control group. Again, d0, which is the 0 here, and the denominator is related to the sample variance of the treatment and the control group and the number of the each group. And we can see that the degree of freedom here, since we have two groups, it's going to be n1 plus n2 minus 2. In the previous version, we had just one group, n1, n, which was n minus 1. Here we have two groups, so degree of freedom is going to be minus 2. And if fast, the point is, we have another assumption here. If we have the equal variance between these two groups, we need to use this formula. If we are assuming there is a non-equal or unequal variance between these two groups, we need to use this test, and we need to use the Welsh Satterthwaite test, which we will see in the SAS output. So this one, it's gonna be a pooled. You can see this keyword pooled in the output. We will see. For this one, we will see the Welsh. So we will see in the example. Uh, let's run this group, this data. So ODS HTML again is gonna just create the HTML report for us. Graphics on. We have the more graphical version. So first, I would like to run the proc univariate for which data, hard data from the SAS help, the default data set that they have in the SAS. The variable is weight. We are classing based on the sex, male, female, and then run in order to check if the data is normally distributed and also check other statistical things. And then this time, again, proc t-test the data, again, SAS help from the hard from the SAS help library, variable is weight, the class sex, and run. So that's the result that you will receive. First, for the first part, for the product univariate, we can see that for the female and male, for the female, the skewness is 109, less than 2. 2.72 is a little less than, greater than 2, but it's still acceptable. We can see in the output in the figure right now that we can see the data is a little skewed. And also for the male version, the skewness is 0.4, 0.28, so they are more normally distributed. The average of the male is 165 pounds. The average of the female is 141. And also this is under basic statistical things. And then here, as we see, this is the t-test, okay? So you remember the pooled and the Satterthwaite or Welsh Satterthwaite I mentioned. So this is the number of observation for each group, and it's gonna calculate both version for us, pooled and Satterthwaite. Pooled for the equal variance, Satterthwaite, Welsh Satterthwaite for the unequal. In order to know that which one we should check, we have to first go to the equality of variance table. Okay, for the equality of variance table, this one calculate if there is equal variance between these two groups as a null hypothesis, or there is an unequal variance between these two groups. Okay, right now we can see that the p-value is 0.0503, almost equal to 0.05. Okay, but it still is greater than that one. So if it's greater than 0.05, that's a cutoff point. Just remember it and just memorize it. Uh, if the p-value is greater than 0.05, we cannot reject the null hypothesis, which means the variance are equal. If we had the p-value less than 0.05, we could reject the null hypothesis, which means we could say, okay, there is a difference between the variance of these two groups. Okay, so now if this is the now, well, because we have greater than 0.05, we cannot reject the null hypothesis. Okay, so let me just yes, we cannot reject the null hypothesis, so we have to go with the equal version of the variance. Now for the equal version, the t value is minus 36, which is very high number, uh, the absolute value, I mean. So technically, the cutoff value for that one was minus 196 something. So we have that value, absolute value, greater than that one. So we can reject the null hypothesis. And also, we can see that the p-value is far away from the 0.05. So p-value is less than this number. It means there is a significant difference between male and female weight, and we can reject the null hypothesis. So these are just the two different links that it's worth to look at. This one related to the t-test, this one related to the effect size. So make sure also to just see these two links. But regarding the t-test, whatever you need to know, you already have it in this video. So again, make sure to watch the video completely, run all the syntax, try to understand the result, and also let me know if you have any question. Have a good one.